Hello everyone. So I apologize that this is the way that we're going through our second lesson of the year. The way that you're getting the notes is digitally, but hopefully a lot of this is review, so it's not going to be the worst thing in the world. I hope that I'm able to impart at least some ways that this will be a little bit easier to work with, especially when we get to the unit circle things. I'll start with this idea of degrees versus radians, of course, but why it is maybe that radians would ever be more useful to us for those who didn't understand when you were introduced to them last year, why you would ever choose to stay in radians. And to mention from that Kahoot that we had the very first day, that whole how many degrees are in 1 radian, and everyone said 180, but oh wait, no, it was actually some number that was a little less than 60 degrees. Why is it that a radian is called what it is? Where is the definition? What does it come from? The definition does not come from pi. The definition comes from the fact that we're talking about the measure of a central angle. If you remember back in AAG, or if you've tried to forget, central angle is when we have that actual point at the center of circle A here. Central angle is the one that when it opens up is going to form that loveliness where those two radii connect to the outer arc. The measure of this central angle which intercepts an arc. An intercepted arc simply means as this angle opens on up, creates this thing, angle BAC here, the intercepted arc is the one that's caught in between. The part of the circle that is on the very outside here that connects those two dots together, it intercepts the arc that is equal in length to the radius. And what that means is that green highlight that I just made for B to C is the same length as that one I just made from A to C. Those two are exactly the same length. 1 radian is the angle that makes that happen. And therefore, when those two quantities are equal, when R equals S, and just to give you an idea, R, we're talking about our radius here. S, the reason we use the letter S, we call it sometimes the subtended arc. S just simply means arc length. So when R and S are the same, you have an angle of 1. When we say an angle of 1, I don't say degrees, I assume radians. Radians, as we're going to talk about in a minute, don't have units. So if I just say that this angle is pi, that assumes that you are in radians. If you said pi degrees, congratulations, you have a 3.14 degree angle. This is actually going to help us define how we can find that theta, though, how we can find how many radians that angle would be based on the fact that, well, if we are talking about this as a ratio, yeah, 1 radian is when those two are exactly the same. But in general, those radians are calculated by taking that intercepted arc length, dividing it by the length of the radius, so S over R. That little star that I have there is just a note. Since we're talking about length divided by length, centimeters divided by centimeters, feet divided by feet, those units are going to cancel out. When we say 1, we don't say 1 radian, we can just say 1 because in theory and technically, radians are unitless. So when I say theta equals pi, you don't ever hear anything after that, you are assuming that it is in degrees. Now, yes, when we were talking about the idea of converting from radians to degrees, we always did say that 180 degrees was equal to pi. And you had your lovely formulas of if it's in radians, multiply by 180 over pi, you get degrees. If it's degrees, multiply by pi over 180, and it equals radians. Or the easier way, generally, whenever you were trying to go from radians to degrees, you would, well, cancel out pi and multiply your angle by 180 to get into degrees. If it was in degrees, you'd divide by 180, and then you'd tack on a pi at the end. So that's how, 30 degrees, 30 divided by 160 is 1 over 6. Multiply by pi, you get pi over 6. That sort of thing. That was the easy part. Now, what you're going to see for the rest of this page is if we chose to use radians instead of degrees, that's actually going to make things a little bit easier trying to find this whole length of an arc, area of a sector thing. You can ignore those numbers. That's just a little code for me to know where to erase. Back in AAG, you had a lot of weird formulas for this. To find the length of an arc, it was theta over 360 times, well, we have to remember our circumference formula of 2 pi r. And the area of a sector was, it looked like the same thing, except this time you multiplied it by pi r squared, or sometimes you saw it as a proportion in either of these cases. The Area of the sector over the area of the circle is equal to theta over 360. All that stuff is absolutely lovely. If your angle is in degrees, that's what you have to do. Having these formulas not in degrees, having our angles in radians actually is going to make this a much easier process because of this lovely formula over here. We are saying that an angle in radians is equal to the length of the arc divided by the radius. We're about to come up with a formula for the length of an arc. That means I want to get s by itself, and that means all I'd have to do is multiply both sides by r. And that gives us a much nicer formula to look at here where we can say, if I want to know the length of that arc, I multiply my radius by my angle and I'm done. As long as that angle is in radians. Not degrees this time, but would be in radians. So if I had that as, let's say, pi over 4, I'd multiply that by my radius and I'm already done. No need to do the weird conversion, no need to do the cross multiplication. Just leave it in radians and you are good. Now, for area, it's a little bit more challenging, a little bit more complex. I won't go into the derivation right now of where this formula comes from, but same deal. Just like for the length of an arc, the only things you would need to know to find the area of that sector are the radius and theta in radians, and that's it. Now, again, please notice that when you go to find an area here, your area is going to be in feet squared or inches squared, and that's immediately going to come from r squared. Again, theta is unitless, so multiplying that by feet squared isn't going to change feet squared. Just a little bit of a note about these formulas, and that would be you can always sort of combine these two together, like how this is r times theta and this is r times theta. That actually means there's a nicer way that we could choose to write this depending on the information that we have. That there's a way to find the area of a sector without knowing an angle at all. As long as you know what the length of the radius and the length of the arc are, you've got your formula right there. And that makes this look even more like the formula of an area of a triangle. Kind of makes sense. This slice of pizza looks like it wants to be a triangle over here, but, you know, not quite. But we can sort of use our two formulas in tandem to make that happen. The rest of this front page, I'm going to leave for you. Based on the formulas that you see here in purple on my screen right now, each of these 3 questions can be done, and I even added a 3B on here if you wanted to play around with these formulas a little bit to say, hey, don't just find the central angle in question number 3, find the area of the corresponding sector. You can use the angle that you found, or you can use one of those formulas above, hint, hint, to go ahead and do that. I'll be posting the solutions to these online probably within the period, hopefully by the end of the period, just so you have this entire packet in front of you. But I did want you to look through these on your own a little bit first. Try them out, see how you do. Remember units at the end if you could. But again, you're basically just using those formulas. This front page, these 4 problems are kind of just, hey, here's a reintroduction of radians, why they might ever be useful. But in terms of where they come from, that's what you saw at the top. The, I think, part that you are most looking forward to would be what we see on page 2. Getting this unit circle thing down again, understanding it where it comes from. Now, I'm not going to say that I know what you did exactly with the unit circle last year. Some teachers do it different ways. Some teachers, say memorize this, that, or the other. There are 16 points on this unit circle, and in my professional opinion, in order for you to understand this unit circle in full, if I was going to ask you to memorize anything, you need to know 2 points. And if you can create 2 points, maybe 3, you'll see what I mean by that in a second, on the unit circle, you can create the entire rest of the unit circle without doing too much work. The first thing I'm going to do is just remind you of our radians conversions. I'm going to eventually put the nice notes on the screen so all of this doesn't look as jumbled. But 0 degrees is 0 radians. We know that much. I've already mentioned to you, we've already talked about it a little bit, how 180 degrees is pi. And if you forget any of the other angles anywhere on here, what they would be in terms of radians, just think of how you would compare them to that 180. For example, 180 divided by 90 is 2. 90 degrees is pi over 2. I think it's probably easier to work with the smaller numbers, the ones that you know, and you love the first quadrant so very much because, again, we're used to those angles. 180 divided by 60 is 3. 180 divided by 45 is 4. 180 divided by 30 is 6. So coming up with those is not so bad. Well, if you can recognize that here's 60 degrees, and now I will double 60 degrees, that's 2 pi over 3's, that's 2 pi over 3. And you can just continue rotating your way around, understanding how these things work. I'm not going to fill everything in, but I am hopeful that you're going to see a relationship between where a point is in terms of like relation to the x-axis perhaps, and what you can see about those fractions. We'll talk about that in very, very specific detail in just a minute. Now, the unit circle is called that because we are talking about having a radius of 1 unit in the coordinate plane. Anywhere I decide to take this line and draw it, whether it's here or down here, or hey, how about this? We are talking about a radius of 1 unit. And if that's the case, then to go from the very center of my circle, the very center of my graph, the origin, out to where I am at 0 degrees, I go 1 space to the right. My x value increases by 1, and I don't move up or down. When I said there are 2, maybe 3 points on the unit circle that you have to memorize, this is the maybe. Because quite honestly, I don't think that's that hard to say if I'm going out in this direction by 1 space, I'm at 1, 0. The others, yes, they're going to be a little bit more challenging. The ones that aren't exactly on the axes, they're going to be a little bit tougher. But thankfully, if you are confused about where these ideas come from, let's talk about how we can develop. We'll start in the first quadrant. We like these angles. They're nice and easy. And why it is that the point that you would always put at 30 degrees was the way it was. This is math analysis. We're not just about, hey, here's where it is, memorize it, know it, good. Once again, we are talking about a unit circle with a radius of 1, whether we put it here or whether we put it here. And so with my radius of 1, I am now looking at a 30-degree angle, creating this lovely right triangle that I've just shaded in. Oh, wait, this is a right angle. Oh, wait, what we have here is a 30, 60, 90 triangle. And if that's the case, and you have the hypotenuse of a 30, 60, 90 triangle, we just have to remember how to work our way backwards and find the shortest side. And that was always to take that hypotenuse and divide it by 2 to get a 1/2. To then find your other leg, you take your short side and you multiply it by, every single special right triangle involved a radical of some sort. And in this triangle, it was a radical 3. So here's my radical 3 over 2. All of this to say, a 30-degree angle, my horizontal line, my x value is root 3 over 2. My height, my y value is 1/2. There I am at 30 degrees on the unit circle. If I don't remember those numbers offhand, I can create this triangle at any time. Get those same values on there. As long as I remember the unit circle has a radius of 1, I'm good to create the rest of it. So there. One point that I would say maybe it would be in your best interest to quote-unquote memorize. We'll talk about how we can more easily do that. But let's get to our other triangle instead. We continue our spin. We would go up to 45 degrees next. We get this lovely thing, but again, we have a radius of 1. And if we have a radius of 1, the question again becomes, in a 45, 45, 90 triangle, how do you go backwards from a hypotenuse to the shortest side? We're always dividing when we go from something longer to something shorter. And as I said, every special right triangle always involves a radical. If there's only one number we're going to be dealing with in this triangle, it's got to be a radical. And that was a radical 2. This one does require a little bit of knowledge of reminding yourself that 1 divided by the square root of 2 means, oh yeah, just like we talked about last time, you might have to rationalize the denominator here and there. Square root of 2 on the top, 2 on the bottom, and you get yourself the length of both your height, and because it's a 45, 45, 90, a right isosceles triangle, your x and your y values are exactly the same. This was the easier point to memorize because, well, you don't have to memorize much. You just have to keep that radical 2 over 2 and do it twice. In terms of points that it would be helpful for you to know when you work with a unit circle, here they are. This is it. If you can create this much of the unit circle, You can now use your ideas of how math works, use your knowledge of how we're going to relate these things together, to simply say, all right, we're going to fill in the rest right now. Let's finish off that first quadrant where we've got 60 degrees. And if I wanted to go ahead and draw myself a special right triangle here, I'd have a 30, 60, 90 triangle with a hypotenuse of 1. We've already drawn a 30, 60, 90 triangle with a hypotenuse of 1. It was what we used to find our 30-degree angle. Well, you remember what we've been talking about a few times as well, the idea of cofunctions, that sine of 30 is the same as cosine of 60, that the y value of 30 degrees should be the x value at 60 degrees, and vice versa. If it's the same triangle, we should be using those same numbers. You don't need to memorize the 60-degree angle if you've already memorized the 30-degree angle. They're the same coordinates, just in reverse. Likewise, when you get to 90 degrees, I'm hoping you recognize this says go from the center straight up. There's my 0, 1. Okay, that part's not so bad. There's still an entire 3 corners of this unit circle, but here's where radians actually come in nicely. We talked about how pi over 3, I double it, I get 2 pi over 3, and I'm over here at 120 degrees. And I have 2 angles that have the same distance away from the x-axis. You may remember this last year as what we called the reference angles. Reference angles talk about how far you would have to go to get back to the x-axis from wherever it is you might be. Reference angles were always acute. So no matter what happens, whatever quadrant we're in, we're always trying to compare to one of those acute angles in the first quadrant. That's great news because those are going to be very easy for us to drag over to other places. The only thing that you have to worry about in other quadrants are negatives. Because now that we are going into our second quadrant, quadrant 2 of our graph, the top left, please remember that anytime you have a coordinate point up here, your x value is negative because you're moving to the left of the origin. Your y value is going to stay positive. And you can already see I'm sort of giving it away by the color here, but if I'm talking about something that is 60 degrees away from the x-axis, I would want to use this 60-degree angle from the first quadrant and compare it. And if I can do that, I can circle around and do this with every single other point. Here is 45 degrees away from the x-axis in quadrant 1. Here is 45 degrees away from the x-axis in quadrant 2. I am in quadrant 2, so my x value is negative, my y value is positive. But since it's a 45-degree reference angle, here's my radical 2 over 2, my radical 2 over 2. All of those other points that you see in this unit circle are going to use the exact same numbers as what you see in quadrant 1. The only change when I get down to quadrant 3, at a 45-degree reference angle, I need them both to be negative. That doesn't change the fact that for 225 degrees, 45 degrees away from the x-axis, I'm still using radical 2 over 2 twice. 315 degrees down here in a quadrant where x is positive but y is negative, and using the same exact numbers over and over and over again. Excuse me. The unit circle, therefore, and let me just go ahead and give it away by going back to this lovely screen, is simply a repetition of all the things that you have from quadrant 1 flying into all the other quadrants. I am not going to ask you to do any sort of like, hey, here's 2 minutes, fill in all of these different things with cosecant of 210 and secant of 240 and things like that. I'm going to say, well, in order to create the unit circle, you don't have to know a heck of a lot. And once you have those points down, once you can relate any of those points in quadrant 4, quadrant 3, or quadrant 2 back to just these 3 angles, let's just go ahead and do that. Let's just try our best to always refer back to what we see from a 30 degree, a 45 degree, a 60 degree angle and work from that. Everything else is pretty straightforward in terms of quadrant 3, negative, negative. Quadrant 4, negative, positive. Oh, my angles that actually lie on my axes, I will always be 1 unit away from the origin, and I'm either not moving up or down, or I'm not moving left or right. Again, you'll have these notes in Google Classroom soon enough, but just so that you're aware, all we need is to find those points in quadrant 1, create them using your special right triangles if you don't remember them, or you've got different little tips and tricks you have here. Here's 0, 1, radical 2, radical 3. Technically this is radical 4 over 2 because radical 4 is 2 and 2 over 2 is 1. And 0, 1, 2, 3, you get the point. You could always try to memorize it that way. The great news about every single one of these fractions though, denominator's not going to change. All of them, in all of our special right triangles, we have this over 2. It's going to be great. Cool. So there it is, your lovely unit circle and all of its fun stuff. It's really not as bad as you want to give it credit for. If you struggle with this last year, again, this is what you need. If you can get this much done, and again, I don't even need to have this entire quadrant on my screen, just really 30 and 45. If you can create those, you're going to be able to create every single point in the rest of this unit circle. Now, as a reminder, why do we learn these points to begin with? What is their usefulness? Well, that's the second half of this page. Consider the triangle at right, sine, cosine, tangent, cosecant, secant, cotangent. This is now for just a general triangle, not necessarily even a unit circle, but any radius. Well, anytime you have that radius and you've got a point at x comma y, congratulations. X is your horizontal distance, y is your vertical distance. And so if we're going to place SOHCAHTOA with this thing, sine is equal to opposite of the angle over the hypotenuse. Cosine is adjacent of the angle over the hypotenuse. Tangent is opposite over adjacent. We know that. Likewise, we know how it works with our reciprocal functions. And because I'm boring, they're always lining up. There's tangent and cotangent. Cosecant is the reciprocal of sine, etc. But since we do have a unit circle, when we're going and making those points, we have a unit circle with a radius of 1. Congratulations. Anywhere I see the letter R now becomes the letter 1. Wow, the number 1. And therefore, sine of theta on the unit circle is y over 1 or just y. Cosine of theta is equal to x over 1 or just x. And that's going to make things a lot easier for all of those lovely coordinate points that you have to worry about. Because if you have that down, then say hello to every single point on the unit circle, which gives you the value of cosine, followed by the value of sine. And if I can just stop for a second and mention how this is the most common mistake that students make, is the order of a point on the unit circle. Most students, when they make a mistake, will say that a point on the unit circle is sine comma cosine. Because every single time that we've mentioned the trig functions in the past, even in SOHCAHTOA, sine comes first, then cosine. The buttons on your calculator, sine is on the left, then cosine, then tangent. It's very easy to forget that sine is supposed to be y, cosine is supposed to be x. Cosine comes first in this coordinate point. So let me go ahead and give you the spoiler for every coordinate point that you will ever draw. It's always in alphabetical order. X then Y. If you ever saw like A comma B, you're thinking the same sort of thing. Here's my cosine comma sine, and C does come before S in the alphabet. So when you get to those points on the unit circle, please do remember that. Cosine, then sine. That's going to be the thing that most people mess up. You can draw a perfect unit circle with all of those points in the exact right places, all of those coordinates in the exact right places. But if you mess it up and say sine comma cosine, obviously everything you give me after that is going to be wrong. So, same deal. Keep in mind, of course, what we talked about tangent on the first day, how it was sine over cosine. Here you see the same reasoning because, well, y over x, sine over cosine. So just another reason why it is that that tangent value does involve having to know what sine and cosine are. All of that to say, here's page 2. Here's going to be the one that, of course, you're going to want to see the most of. Here's your completed unit circle. Here's your, I've got my notes on here, blah, 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 blah. Yeah, pause the video and copy down as much as you'd like, but this will be in Google Classroom anyway, so let's not worry so much about that. In terms of how the trig functions behave, you do have to remember some things about positives and negatives. Now, you could always memorize it based on the unit circle, what the coordinates are, but we also had that lovely mnemonic device of all students take calculus to decide, hey, here's how we can decide what's going to happen in all of our quadrants. Now, quadrant 1 is easy enough. Everything is always positive in quadrant 1. All of our trig functions are positive. The only reason I'm stopping and making sure to go over this is please do not say the words, the only trig function that is positive in quadrant 2 is the one that begins with an S, which is sine. That is not the case, and you also need to be careful because there's another trig function now that begins with an S. Yeah, sine is going to be positive in quadrant 2 because we said sine is our y value and my y value is positive. But if sine is positive, then so is its reciprocal. So don't just say that in quadrant 2 sine is positive. Sine and its reciprocal, cosecant, would also be positive. And then yes, you can say, well, now if we're in these other quadrants, if it's positive, great, all the others have to be negative. So in each of these quadrants, I don't want you to think of one of them is positive, the other 2 are not. It's 2 of your functions are positive, the other 4 are not. And of course, to give away the rest, all students take, we're talking about tangent, the only trig function that begins with a t, luckily, but cotangent would be positive there as well. Quadrant 4, the leftovers, so cosine and secant, all positive, all the others would be negative. Again, if you've got the unit circle kind of committed to memory, you're forced to have answers that look like this because, well, if you are asked for cosine of an angle in quadrant 4, your x value is already positive, you're done, it's positive. But it is something good to keep in mind when you're, not staring a unit circle in the face on your screen, or you have to try to create this in some sort of different way. You'll notice these next 6 questions. We'll go over these. That'll be it for me, and I'll give you their homework from this other packet that you have. As we go and say, let's analyze these things. For cosine and sine, there's not a lot of analysis to do. If you have a unit circle, feel free to go ahead and read that right off of your unit circle and figure out where it is. I'm going to say, if I don't happen to have this whole thing completed in front of me, then there's a nice and easy way that we can consider this by only talking about the quadrant that we're in and the reference angle that we see. And really, the reference angle is the important thing. You see this thing that says the quadrant? All that is going to impact is what you see in the top half of this page. A quadrant only tells you whether your function is positive or negative, nothing about its value. Everything else is going to depend on this reference angle of theta. The wonderful news about these 6 problems is that your angle is in radians for all of them. And radians on the unit circle make your life incredibly, incredibly easy. Because all you need to know to decide what your reference angle is, all you need to compare to here to see what your reference angle is what number you see in your denominator. Any angle that you have in its most reduced form that has something over 3, congratulations, your reference angle is pi over 3. In question number 5, your reference angle is pi over 6. And if you can come up with, or at least very quickly remember, what the angles are for pi over 3, pi over 6, come up with what your sine or cosine are for those, the rest of this becomes very easy. I know that pi over 3, 60 degrees, is 1/2 comma root 3 over 2. Cosine is your x value. So, cool. My answer is going to be 1/2. But I just might need to decide if it's positive or negative. And that's where I would have to actually analyze and say, what quadrant is 4 pi over 3 actually in? The easiest way that you can determine what quadrant something is in is to decide what this fraction is. My fraction of 4/3 is a number that is slightly larger than 1. This angle is slightly larger than 1 pi. And I'll go ahead and I'll look at my unit circle and say, here's 0 pi, here's 1 pi. I know I'm greater than 180, but I'm not quite as big as 3/2. 4 pi over 3 would have to live in quadrant 3. In quadrant 3, cosine is negative. So this idea of use the quadrant and the reference angle allows you to not have to remember that 240 degrees is the point negative 1/2 comma negative root 3 over 2. It allows you to just say, oh, well, let me go to the answer here. As long as I know that cosine's got to be negative, I have my reference angle because it's a 3 in the denominator. When given in radians, the reference angle is the same as what you see in that denominator. Congratulations. Cosine of pi over 3 is cosine of 60, which is 1/2. I just know it has to be negative because that's what happens in quadrant 3 for cosine. And so this idea of evaluate by using the quadrant and the reference angle simply says, oh, okay, I've got a reference angle of pi over 6 because it's a 6 in the bottom. 7 over 6, though, that's a little bit bigger than 1 again. We're still in quadrant 3. Sine is negative there as well. Take my answer and make it negative. So when you have these sines and cosines and you're just reading them straight off the unit circle, that part's easy enough. The other functions, of course, get a little bit more complicated. You can see over here all the different ways we do this. Tangent, you're going to actually have to take your two values and divide them. That's what's going to make tangent, generally speaking, the hardest one for you to find. Again, you might get to the place eventually where you just memorize what tangent of pi over 6 is, but as a reminder of where it comes from. First of all, I've already given away. We're talking about a pi over 6 reference angle. We're talking about the point root 3 over 2, comma, 1/2. Okay, it's time for us to say that to find tangent, I have to do y over x. And y over x is equal to 1/2 over root 3 over 2. We have to take two fractions and divide them. Here's the lovely thing about the unit circle, though, and I've mentioned it already. Your denominator for the unit circle for these points that are in the first, second, and third quadrants, and fourth quadrant, they're all going to be 2 on the bottom. That means when you take your fraction divided by fraction, you turn it into a keep, change, flip scenario. When you flip those fractions, if they have denominators here that already match, congratulations, you're going to take those denominators and cancel them out every single time. When you have to do tangent or cotangent, and you have to divide your two coordinates by one another, you get to ignore those denominators. And just say, you know what I'm actually going to do, since those are going to cancel out, I'm just going to say that this is 1 over radical 3 and reduce it however it is, or rationalize it however it is I may need to. And once I have that, the only thing I then have to calculate is, where am I? 5 pi over 6 is in which quadrant? 5/6 is a number that is slightly less than 1. Here's my 1 pi. Here's my slightly less than 1 pi. And in the second quadrant, tangent once again is negative. So it's a lot of comparing to what you've seen before. It's a lot of, hey, let's just remember what we can remember about quadrant 1. That makes filling everything else in just fine. I'm not going to say you can't memorize the entire unit circle every single time. It's going to create a lot of extra work for you to just, sketch an entire unit circle on every single trig test or assessment that you would ever do. The more comfortable you can get with just what's happening in that first quadrant and reproducing it for whatever you'd have to do in the other quadrants, the quicker you're going to be able to get through these problems. Cosecant, secant, cotangent are the same types of questions, and I'm not going to waste too much of your time right now. I'll show you the same idea for those. It's still going to involve, in some cases, needing to rationalize a denominator when you try to take something and flip it upside down. Like, for example, secant is the reciprocal of cosine. Yes, I'll have to do root 2 over 2 and flip it. The reciprocal of 1 is 1, so that's pretty nice for cotangent. But keep that in mind as well. You'd have to flip your tangent value, or just remember that if tangent is y over x, cotangent is x over y, and you don't have to worry about reciprocals there. Some of your fractions, though, in the unit circle will be a little bit challenging, namely the reciprocal of root 3 over 2. Those are the ones that look the ugliest, but the nice thing about it is you don't actually have anything that cancels, so negative 2 radical 3 over 3 looks like a lot, but in the end, it's not quite as much work as you might think. You don't have to worry about keep, change, flip. You don't have to worry about any of that other stuff. What you do have to remember is you have to decide what the sign is going to be. Again, the only difference between getting the quadrant right or wrong will be, do you have a negative sign or do you have a positive sign? And I'm not taking a whole bunch of points off for that if I see that on an assessment, but of course, for number 8, 1 is incorrect, negative 1 is correct. So please keep that in mind. So again, I'm going to be sending you notes for all of this so far up through question number 9 of this packet, because this is all I'm going to ask you to do now on your homework. I'll go to my trig 3 exact functions of trig values thing, and I'm going to be sending you notes on this to see, all right, follow these steps. It's basically what we just talked about on the previous page. If you want to know where you are in the unit circle, if you want to know how to find cosine of 11 pi over 6 or cosecant of 3 pi over 2 or anything like that, figure out what quadrant you're in, figure out your reference angle, and then if you don't know the unit circle, you can still build that special right triangle wherever you are. Or you can recognize by the reference angle, I can build that special right triangle in quadrant 1 and then just apply a positive or negative sign depending on what my answer is for the quadrant. And so since all of our stuff comes from these same unit circle special right triangles, we're still going to run into those same sort of ideas. We're still going to have our now bouncing between radians and degrees. You might feel more comfortable leaving it in degrees. If you see it in radians, now that you know that the reference angle is always going to be something over 3, something over 4, something over 6 is going to be very helpful, by all means, stick with that. And in the notes that I've given you so far, I am, and what I will attach in Classroom, I should say, I will give you the first question. For cosine of 30, okay, I could memorize the unit circle and just immediately get it off of that, or remember, hey, it's its own reference angle. That's not going to be too bad. Maybe I should have done the first example as something a little bit more challenging, but I can still just decide if I don't remember radical 3 over 2 comma 1/2, I can always just create myself a special right triangle and do it. And even if I use the rules of special right triangles and I don't use a unit circle, either way, when I do adjacent over hypotenuse, those x's are going to cancel out. I'll get myself a root 3 over 2. So you've got the option available to you for how you're going to do this. I am going to ask you for homework, and I'll have the attachment in Google Classroom where I want you to upload an image of your work. Question number 1 up through, I'm not going to give the rest away, up through, let's say, question part M. Yeah, that sounds about right. So I'm going to be giving you the notes for cosine of 30. I'm going to ask you to do the next 12. Just see how you do with them. If you're feeling confident, if you're feeling great about it, by all means, try to complete the page. By all means, try to move on to the next piece. We'll talk about the other questions, 2 through, 7, 8. We'll talk about those on Wednesday. But for now, hopefully this is just a little bit of a reminder. Hopefully this is just some guidance on where it is that these lovely numbers came from, why it is that they were the way that they were. And again, if this is the hardest thing that you have for this unit, great. It is something that you can very easily reproduce on your own with a minimal amount of effort, and then just literally reflecting your points across the x and y axes to get to where you need to go. I hope this has helped a little bit. Again, I'll post the homework on Google Classroom that you have for it, and I am sincerely sorry I wasn't able to be there with you in person for this. If you have any questions about anything you've seen with this, please, by all means, send me an email. I will try my best to get back to you within the day. And when we reconvene about this on Wednesday, hopefully the idea will be a little bit easier to work with. We'll get a lot of practice with this online. You have some more practice on this packet as well. Hopefully it works out okay. So thank you all. I hope to see you again very soon.